Okay, for tutorial 5. Now, problem 1.1, length required for cooling coil. A cooling coil made of copper tube is immersed in a regulated constant temperature bath held at a temperature of 20 degrees Celsius. The liquid flowing through the tube enters at 22 degrees Celsius, and the coil must be sufficiently long to ensure that the exit liquid sustain a temperature of 20.5 degrees Celsius. The bath is so well stirred that the heat transfer resistance at the tube bath interface is minimal, and the copper wall resistance can also be ignored. Thus, the tube wall temperature can be taken equal to the bath temperature. Use equation 1.17 to estimate the required tube length under the following conditions for the flowing fluid. Okay, so you are given the information here, and since the Reynolds number is in the turbulent range, we can use the correlation of Cedar and Tate to calculate H. Okay, where you are given the Nusselt number, Prandtl number, and the Reynolds number. Okay, so how to approach to this problem? It's very simple. Okay, wait a moment. Now you have been given that Tz minus Tw divided by To minus Tw equals to the exponent of negative 2 pi RHZ VO A rho CP. Alright. Now, if we want to estimate the length, meaning to say we will have to calculate for Z. Okay. So in this case, since we want to calculate for length, Z equals to L. So TL, we change this one to TL minus TW over To minus Tw equals to 2 pi RHZ VOA rho CP. Okay, then we can calculate for the Nusselt number. Okay, now because we have all the information here except for H, so how can we calculate for H? We can use the Nusselt number. We have this formula given. Okay, we will use this to calculate for H. But we need to know the Nusselt number first, so we can calculate the Nusselt number from here. In this case, we need to identify the Reynolds number and the Prandtl number. Okay, but this one can be easily calculated by slotting in the information. Okay, much better. Now, oops. Now, we can write down the equation for the Nusselt number first, which is H multiplied by the diameter, which is 2R, and R is 0.01, so the diameter is 0.01 0.02 meter divided by 1.43 times 10 to the power of negative 4 kilocal over S and K. Okay, now for the Prandtl number, we can calculate Cp mu over K, so Cp is 1 kilocal over kg per degree Celsius multiplied by mu 0.001 kg per meter second divided by K, which is 1.43 times 10 to the power of negative 4 kilocal over second per meter per Kelvin. Okay, because we have Celsius and K over here, right? So we need to change by putting 1C is 1K. Therefore, we get 6.993. Whereas the Reynolds number is the diameter, velocity times the density divided by mu, which is 0.02 meter multiplied by 1 meter per second multiplied by 10 to the power of 3 kg per meter cube and divided by 0.01001 kg per meter second. Okay, so everything can be crossed off. This is meter cube, this is meter second, yeah. Meter cross off, second cross off. We get 20,000. Okay, now we then calculate for n, the Nusselt number, which is what's the 0.026 multiplied by the Reynolds number 20,000 to the power of 0.8 multiplied by 6.993, which is the Prandtl number, to the power of 1 over 3. Okay, then we can substitute this back to this equation here. Yeah, so over here we should get 137.199. Okay, so by substituting, taking this, the value here, where's my cursor? Okay, 137.199. So over here we get equals to 137.199. Okay, then we can easily solve for the H. H is 0.981 kilocal per second meter square Kelvin. Okay, so we have our H, we can substitute it here, and we can solve for Z. Okay, so then we want to identify what is our TL, TW, TW, and what is our T0. Okay, so our TL is 20.5. Okay, the exit liquid should have this temperature, so this is TL, and the T wall is 20 degrees Celsius. Okay, and TO, which is the temperature when it enters, is 22 degrees Celsius. Okay, so enters is TO, right? TO is 22 degrees Celsius. T wall is 20 degrees Celsius, and TL is 20.5 degrees Celsius. So substitute the value back in, okay, to the equation. So we get 20.5 minus 20 degrees Celsius divided by 22 minus 20 degrees Celsius equals to exponent of negative 2 pi, r is 0.01, h we have found, which is 0.981, 0.981, okay, multiplied by L over here, divided by VO is 1. Okay, now in your exam you have to write down the units over here. For example, 0.01 meter. You need to write this down, okay? But in this case, I'm not writing it down. So this one is 1 meter per second times A, okay, the area. So the area is pi r squared. And multiplied by the density, which is 10 to the power of 3, times the heat capacity, which is 1. Okay, then we can easily solve for L to be, the length required is 7.064 meter. Okay, now moving on to part 2. Now, the cooling of fluids in tube flow locally varying H. So we apply the conditions of Model 1 Plug 4 in Tutorial 5, and we derive the expression for the temperature change when heat transfer coefficient is not constant but varies according to the law of this. Okay. Okay. In this case, the energy conversion law for Model 1 plug flow leads to VOA rho Cp dt dz plus 2 pi RH multiplied by Tz minus Tw equals to 0. So we have, in previous problem, we assume that the H is constant, but in this problem, H is related to this equation instead. Okay, so we plug in H in, we plug the H in, so we get VOA rho Cp dt dz plus 2 pi r. H is over this. Okay, and okay, now we divide everything by this. Okay, because we want to let this stand alone, we divide everything by this and put the constants on one side. So dividing this by this, we get nothing. So over here we get dt over dz plus 2 pi r gamma over VOA rho Cp. Okay, and you have your 1 over square root of z multiplied by t z minus tw equals to 0. So we define a new parameter here. Okay, so meaning to say, okay, this one, okay, we will define it as beta. Okay, and this one we will define it as theta. Okay, so we have our, so in this case tz minus tw equals to theta. Okay, so that leads to d theta over dt to be 1 and giving d theta to be equals to dt. We can substitute d theta over here since we are defining the new variable theta. Right now, so dt is d theta, so we change. This one should be d theta over dz, okay, plus, okay, beta over here, beta over square root of z multiplied by theta, because we have defined this one as theta equals to 0. So this gives us d theta over dz equals to negative beta over, okay, so we rearrange them. Okay, and we put theta to one side and the rest to another side. So divided by square root of z is negative to the power of negative 1 over 2, yeah, multiplied by dz. Okay, integrate this, okay, integrate theta, and integrate z. So the integration of this gives us ln theta equals to negative b beta multiplied by 1 over 1 over 2, and that here becomes 1 over 2 plus 1 plus c. Okay, and therefore we get negative 2 beta z to the power of 1 over 2 plus c. Okay, and then in this case we take c equals to ln k. We take c to be ln k since it is a constant. Therefore, ln theta equals to negative 2 beta square root of z, put this back as square root, plus ln k. So we bring ln k over, minus and this is actually ln theta divided by k, right? Okay, so theta over k is exponent of negative 2b square root of z, and theta is k exponent negative 2 beta such. Now we can use the boundary condition. Okay, so at z equals to 0, we know that t equals to to. Therefore, from our previous variable definition, we get that theta equals to to minus tw, because initially this one was tz, right? So when z equals to 0, we define it as to. Okay, so we substitute theta back into this equation here. Okay, so the new theta, so this one we substitute this one as the theta here, to minus tw equals to k exponential to b z. Okay, but z is 0. Okay, so over here this becomes 0. Therefore, exponential of 0 is 1. Okay, so we get k to be equals to to minus tw. Okay, so we substitute back into this equation where theta equals to to minus tw. This one was our k previously, multiplied by the exponent of negative 2 beta square root of z. Okay, then we can, for this theta here, it is tz minus tw, right? Oops. Okay, this is better. So this theta we have defined, this is tz minus tw equals to to minus tw 2 beta z. Okay. Rearrange, so we bring this one over and we put back our beta in, which was what we have defined previously. So beta was this, right? So we put it back in. we shall get Tz minus Tw over To minus Tw equals to exponent let's try a big one. So negative 2, so multiply it becomes 4 pi r gamma VOA rho Cp multiplied by square root of C.